So today I'll be talking about AutoML and basically how tools in general obtain quite accurate results uh, using a variety of techniques. I'll talk about some of the tools that are used in the world to do this AutoML trick. And I'll discuss some of the data science best practices that will showcase how some of these tools work. And I'll talk about customizing driverless AI, and because that's one of the ways in which you can really dig into the domain science specifics for your own data. And then I'll summarize. So what should AutoML tools do? And by that I mean, what do they help with? So in general, you're probably familiar with this, but I wanted to give this background to make it clear what we're talking about. So roughly speaking, AutoML tools help with accuracy, of course. They try to make it so that you don't have to worry about whether or not you're going to get the best model. And in particular, which I'll discuss a little bit, you want to make sure that they don't at least give you the worst model. That would be the worst thing, is that you use some advanced tool and you end up getting the worst model that you could get just because of problems with the tool. It also will help with interpretability, which means that it will be able to balance how many features you have against the needs of latency for scoring versus the size of the model, and basically find a balance between all those different things. And in particular, regarding interpretability, something you can control. So hopefully that will be something you're able to do. And it needs to handle diverse situations. There could be many classes. It could be regression, binary, but maybe there are 350 classes, like different outcomes that you're trying to predict. And there may be 350 different kinds of foods that you're trying to predict, or different kinds of commodities. It needs to handle a variety of different kinds of columns, meaning not only count, it needs to be, one column. For example, if it's a one column, one feature, and one target, or it could be a million columns. And not all tools can handle that. Of course, in a large number of rows, or even a very small number of rows. So sometimes you might have a very small data set, and that's very important to you. It doesn't really matter that it's 1,000 rows or something like that. You need the best model. What do you do when you have only 1,000 rows? And of course, it needs to handle the kind of data, different data. And that could be called multimodal. It could handle a variety of types of data like text or categoricals, which look kind of like text, but are more, not a written word of some kind, more like a label, like cat, dog, mouse. And it needs to handle maybe images. It may need to handle actual text, like a natural language processing type model. And it needs to find a balance between all those things, like I mentioned. It needs to also probably help you explore custom aspects that are domain-specific issues for your problem. And of course, a big thing is avoiding mistakes. If you create one of these kinds of tools like I have, you'll find that it's very easy to make mistakes. And I make mistakes all the time. And having a tool helps you formalize things so that you don't make mistakes, like whether or not you have data leakage or something like that. And it needs to be easy to reuse. So when you create a model, you don't want that to be the end of the story. You want to be able to reuse it, study it, deploy it, share it with somebody else. You want to be able to track it as it's performing predictions, and you want to be able to maintain it across a different set of people, like a lot of products do. Another aspect of AutoML is, in terms of what it is how it consumes data. So the very first step is, of course, you need data. And that's an important part of any AutoML tool. And it's not part of every tool. So one is you need to deal with data preparation. You want some kind of feature store that manages the data, and not just a data lake, but one that knows about the importance of the features to a variety of models. And maybe you need to write arbitrary code, like in driverless, you can write arbitrary Python code to deal with data once it's in driverless. And there's, of course, data ingestion. You have a variety of statistics and visualizations about the data. And whenever you're doing AutoML, you need to make sure that the data makes sense. You have to check the training data, the validation data, the test data, make sure the types make sense between all those different sets. Deal with nands, infinities, check the target to make sure it makes sense. Check the time column to make sure it has no missings, because that wouldn't make any sense. Check any weight or full column. And of course, you can check for duplicates, because if you have duplicates, which is quite common in a lot of cases, between, say, the training set has duplicates, that might be okay if it's intentional. But if there's duplicates that are in train, but they also appear in the test set, you probably want to know about that. And we need to determine the data science types. Like, so we've taken in the actual data. We need to determine, is this stringy looking thing that's alphanumeric, categorical, or text-like? And that has to be, that helps cut down on the search space that the AutoML tool eventually has to do. And of course, figure out the date format in case you're doing time series. It should check for data leakage in a variety of ways. It should compute something like AUC for leakage. It could do R² or compute the correlation. And it should check for data shift. Data shift is when you have a training set and, say, a test set, and you assume, let's say, that this is independent rows, what we call IAD, but maybe they're not. Maybe there is some kind of trend in time, perhaps, for example, from the training set into the test set, and you need to know about that and maybe deal with it somehow. And of course, as we've had other talks, in particular, Dmitry Larko talked about feature selection. And one important aspect, even up front when you have too much data, is to somehow reduce the dimensionality if you have a large number of categoricals, how to do that. And then now that you have the data and you sort of prepared yourself for the kind of data you have, you need to make models. And this is just an overview. So you might start tuning, like try different things. This is what AutoML does, but in a more guided way, typically. So you might try a variety of target transformations, changing the target for regression. And then, of course, you might have a variety of models, tree models, linear models, neural networks, NLP models, image models, and they have their own hyperparameters, and you want to, of course, try those. And you might have a variety of features. You want to do feature engineering, and you want to, for example, have the features that were text or something text-like to have some kind of frequency encoding, or like TF-IDF, where it's looking at the actual account of different patterns in the data. And then you have to build, after you've done all that tuning, which is what I'll focus on a little bit later, it's kind of the more interesting aspect of AutoML, you'll build a final model. And that final model might be a single model, might be an ensemble. If you're doing time series, that's when you can do some back testing to determine what's happening across different time slices. You can check the stability of the model. So you can compare the final model to what you were tuning and check and see whether or not the features are behaving appropriately, and that the model across all, say, cross-validated splits is behaving appropriately. And of course, you can generate artifacts for scoring later, like either what we call Mojo in H2O, which is just basically Java code to run in Spark or something like that, or Python code to run on MLOps platform or for local use. And then once you're done with all this, it's not the end of the story. Even AutoML means that you need more than just the model. You probably need documentation, like AutoDoc and Driverless AI. So we generate an experiment documentation, which will tell you what happened in the experiment, which is very useful. It could be, roughly 50 pages of explanations and other kind of things. You probably want model Shapley. You want the Shapley values for the model. You might want to run interpretation through our MLI or some kind of any other tool where you're trying to understand the significance of certain features through partial dependence plots, whether, what the trend versus other features is for the predictions. And you might want to just analyze the model through a variety of metrics, what we call diagnostics. And then, of course, you want to share the model with other people. We do that through projects or import, export. You want to rerun the experiment without having to go through the whole process again. We also call that refit. And you might want to tweak the model. So maybe you like it, but there's one feature that you want to remove. You should be allowed to do that. Otherwise, it's a too black box of a tool. And finally, you want to be able to track performance and maybe swap out models on demand in the MLOps platform. So there are a variety of AutoML tools out there, and you can consider them as, there's like two kind of rough groups. One is open source, and one is kind of closed source or a little bit mixed. Now, open source could include H2O AutoML. There's also a large number of other packages. Some of the most powerful ones, I would say, are AutoSKLearn 2.0. It has a lot of advances, like AutoML, and even Flamel by Microsoft is pretty good. Amazon has AutoGluon, and then there's a variety of tools here. Some of these are not in favor anymore. Like if you say Teapot, there's nobody who would rely only on Teapot, for example, at this point. It was a good starting point a long time ago, but not anymore. And then there are closed source products like Driverless AI, and they're mixed because Driverless AI does provide the full exposure of the Mojo artifact. You can stare at the full contents as if it's open source. We also expose the options within Driverless through Python. You can write arbitrary Python code to modify any experiment. And other companies also provide some access to either looking at the source code or something like that. So there's a variety of tools. So how do you choose which tool to use? I just want to bring up in the recent Gartner, H2O.ai's AutoML use case was the highest ranked, so that's good. And I'll explain a little bit why that is. Why is H2O doing well in AutoML? Why is it doing well in accuracy? But you could say that in reality, 3.7 versus 3.6 that's not a big deal. So the platform perspective is required. How well would this tool work within an ecosystem of MLOps, interpretation, running interpretations, documentation for the use case of any kind of use case of needing to report on the performance of the model, like a review board. So how do you choose? Well, there's always a risk of going into a benchmark war, which we affectionately call it when we're looking at these different tools. And this happens in any field. But there is a nice tool to do benchmarking of AutoML for tabular data. And it was helped put together by one of our chief machine learning scientist, Erin. And she helped with her collaborators put together this website. And OpenML, which I'm showing here, it's a very nice website where you can basically download tens of thousands of different kinds of data. And it's very well annotated. And this particular AutoML benchmark, what part of the website runs any arbitrary tool that you set up on a variety of different kinds of data sets, maybe 50 or hundreds, and it will tell you how it performs. So this is quite important to do, especially at least internally, to understand how your own tool is performing. So this is just showing a sample of how driverless, which I worked on, performs compared to some other tools that I mentioned. And these are just open source tools. Later, we'll have blogs about how we compare to our own other tools internally, like H2O AutoML or other closed source tools. But for this talk, I'll just talk about how we compare against other open source tools that are quite strong. And so here we have, let me make it a little bit more clear. So here we have a table, and it looks like a very busy table. I've chopped it into And we have a variety of different data sets that are shown by name, both on the left and on the right, on the first column. And then it tells you how many rows the data set has, how many columns it has, and how many classes. And all of these, there are 39 data sets here, but all of these are classification type problems where you're trying to classify instead of a regression type problem where you're trying to predict the actual number. So you can see driverless AI here, and what has been done is to take the either accuracy or log loss and try to write it in a way where smaller is better. So this is either log loss for a particular data set after 1 hour of running, or it's the 1 minus AUC, if you know what that means. So we just take the area under the curve, ROC curve, and take 1 minus that. This is what other tools have done in various papers. And so now that you have that, the smaller the number, the better, and you can kind of compare across tools. And one thing you can see is that, well, what I've done is I've made it bold whenever the tool has done the best. And I've underlined it whenever the tool has done the worst. And we tally up those things over here. So there's a certain number of best, a certain number of worst for each tool. This column was driverless AI. This one is Llama. This one is Microsoft's Flamel. And these two are AutoSKLearn. And AutoSKLearn 2 is sort of one of the more advanced tools that's come out in the last year. So at least against these open source tools, you can see driverless does a pretty good job. It's not the best always. There are 39 data sets, so we're best on 20 of them, but we're not worst on any of them. However, some of the other tools, they're always worse on something. So you could ask, well, why is that relevant? Well, let's just say, first thing I can point out is that in some cases, driverless is quite a lot better. For example, in this data set, which has a quite large number of rows, 4 million rows, 60 columns, but it has a large number of classes. That's a really challenging case of about 355 classes. And the log loss, or the basically measurement of how accurate it is substantially better than a lot of other tools. Some other tools just really have problems, such a problem, such a use case. And another case where driverless does incredibly better is this jungle chess, just another kind of problem where it has a certain number of rows, about 50,000, only very small data set, 7 columns and 3 classes. And the log loss is 10 times smaller than any other tool. You can say, well, John, that's great. Driverless does well sometimes, but that's not super interesting because most of the time it's just going to perform similarly. So that's why I mentioned this last thing, which is how often we're the worst. So if you look at some of these other tools, for example, Llama, you can see that in one case, they're not just worse, they're really bad. And that doesn't usually happen, but it sometimes happens. And this is a bank marketing case where you're trying to study whether or not your marketing campaign is going to do well for a particular bank. And you have other cases where other tools like AutoSKLearn does substantially worse. So here we have a case like this jungle chess one where it's substantially worse than all of them. This is supposed to be the most advanced tool, and it's even worse than their prior iteration, AutoSKLearn 1. So the point of this saying all this is that you don't only want a tool, AutoML tool, which does the best, but you don't want it to do worse because you might have an arbitrary use case and you want to avoid the risk of ending up with a model that would have been worse than any other tool. So that's what driverless helps avoid. We spent the time to figure that out. So let's move on to, make sure that, yep. Let's move on to how do you do AutoML? What are the best practices? How is driverless successful compared to some of these other open source tools? And they use quite advanced techniques, but driverless uses advanced techniques, but a lot of the reasons for the behavior, the good behavior, is because we keep it simple. We don't overcomplicate. So for example, when you're doing AutoML, the very first question after you have the data is how should you do the searching of all possible hyperparameters and all possible features. Well, the very simple baseline models that you can make, they can just be very simple. If you have a low cardinality, which means that a column feature has very few uniques, so maybe it's just 4 different values in the column, you just do one hot encoding. That's reasonable. If it's higher cardinality, many uniques in the column, you can do frequency or target encoding. And you want to try a variety of models to see how they perform. At least you know how they perform. That's one of the good things about driverless. It can be a benchmark regardless of the use case. It should be tree methods, GLM, multi-layer perceptron, at least one of each to see how it would perform. And you also need to try cases, well, sometimes though, features can make things worse. So for example, one hot encoding in some cases can overfit and it will do a poor job. So you can't just assume that one hot encoding will work. You need to try disabling one hot encoding or disabling target encoding. And target encoding, by the way, is these different things, I can explain what they are real quick. One hot encoding is just where you take a feature that has, say, a certain number of levels, like say 5, and you turn it into 5 new columns, each with 0 or 1 inside. So you kind of add new columns to tell you which level it was. Whereas frequency encoding just counts how often some number appears in the column. And target encoding literally takes the target and says, for that given value of the feature, what is the target? And it memorizes that. You know, it sounds like a really bad thing, but if you do it very well in a controlled way, it's actually quite good in a lot of cases. And like lastly, you might also want to only do target encoding and no other kinds of encodings. And you also need to like start from that baseline, but you need to have some kind of models which are a little bit exploration. And this is a concept called exploitation exploration. You have to balance these things. You can't only rely on what you've always done. You need to explore a little bit. And so what we do, and this is kind of a common thing, is that you can try a model, use some measurement of its variable importance to see how valuable each column is. And then now knowing that, you can tell the next model to build features that use that fact. So for example, you might want to combine columns together into a new feature, and you can use the top performing features from the prior model to build the new model for that input of the new feature. So for example, target encoding or frequency coding can take multiple features. It takes multiple columns and then combines them into a single string or a value, merges them together, and that's a key upon which you memorize the target or you count the frequency. So sometimes you want to have that higher interaction depth, as we call it in driverless, and you can do that, but you got to be careful about which features you choose because the search space is so large. So you can use what the prior model said to iterate on that and choose those features. And sometimes you need just random features. Sometimes you get lucky and you might run 10 experiments or run a leaderboard, we call leaderboard in driverless, and that you want to see that work. And you might have exceptional situations. For example, wide data, it's very risky. You might think, well, I use a GLM and I have very wide data, which means that you have many, many columns but very few rows. Maybe you have 100,000 columns and 1,000 rows. This is very common in genomics data. And it's quite risky to use anything like a GLM because it will pick out the exact features that work, but will they work again? Will they generalize? And often they don't, because there's always some shift when you go from the training set to the test set, a real test set. So it's very risky. So you want to use a random forest, which is less likely to be biased, even though it has a large variance. And then finally, when you do the search, a lot of different tools do it differently. You could use a genetic algorithm, which basically treats models as individuals. And this is what one of the things driverless does. And this is what Teapot originally did. So basically take every model and its parameters and features is an individual. And then there's a population of individuals, population of models. And you score them. And then you say, well, okay, how did they do? you basically can make them into a competition, maybe a pairwise competition. And if the losers drop out, the new remaining survived individuals will create offspring with a mutation. And the mutation is just a change in the hyperparameter or one additional feature, or maybe removing a feature that was low importance, those kind of things. So that's the genetic algorithm. And they can also share, the different individuals can share features across them. But of course, while you're doing this, you have to be very careful. You need to balance this exploration versus exploitation problem in machine learning. You need to maybe explore early, but then as you dig in and you have a more accurate model, you want to exploit what you've already learned. But then maybe you get the modeling process gets stuck, and then you need to do more exploration. And you can imagine that doing this manually would be quite tedious. So that's what an AutoML tool should do. And of course, while you're doing all this, it's very important to validate everything. You know, cross-fold validation, repeats, which is basically a repeat is where you just change the seed of the different the sampling that used for the cross-fold splits, and it gives different data in each one of those splits. So it's just like a whole new experiment with when you do repeats. And if you have time series, you need to do time-based splits. And even some of the features that we build, like target encoding, it's very sensitive to leakage. It can leak the target into into your data, into your feature. And so you need to do sometimes cross-fold validation within cross-fold validation. It's called nested cross-fold validation. So that's useful. So all these things put together means that in the end, you have a lot of good practices, and that's what we've put into driverless. And so I'll switch the screen now and go to driverless and give you an example of what I was just showing on the main screen. So this is an example run where I just wanted to show how driverless improves. So we have here a plot of the log loss, so lower is better, versus iteration. And you can see at the beginning, it has some kind of log loss of 0.467, which is high, but it's still a pretty good model. It has one hot encoding, target encoding. It's trying to do the best it can still. And it has maybe a little bit more features than you originally have. And then it tries to do the search process that I just described, where we're trying to figure out early on among all these different baseline models, plus some other random models, which one's best. And then it switches gears. It goes into a new mode where it's doing the genetic algorithm. And then it starts doing these mutations and trying things. So you see all these dots up above. These dots correspond to where it's tried something, it didn't work, too high of a log loss. And it's trying to find the best track. And eventually it does a model which is significantly improved compared to before. But you need a tool which, in this case, it has something like 400 features, but maybe that's too many. So you want to be able to control all that. So let me show you an example. Okay, so here's driverless. Usually we have our data set. I'm focusing on the part of the process where we've already consumed the data. And we're thinking about this AutoML. So we might ingest some data set, which has a credit card data set. And we have train and test. And then in driverless, the view is that, well, you can go check this data out, look at the details. I'm just only using the left click. And you can view all the different histograms about the data, the properties of the data. You can look at particular data set rows to actually see the raw data. You can change how we treat the data. You can also modify the data with a recipe. So that is, you can actually generate arbitrary Python code, which I'll talk about in a moment. But once you have that data, you can do a variety of things. You can visualize the data, which I won't get into right now. Split the data in case you want to split the data yourself. But the most important thing for this talk is how you predict. So Arno, the CTO, gave a Masterclass talk a while back, a few weeks ago, talking about what we have is the wizard. The wizard is very nice. It basically makes the process of using driverless very easy. I'm going to show just the standard classic version, since he already went through that, focusing on the AutoML aspect as opposed to the experiment setup process. So we run predict, and predict means that you're trying to do something with the data, that's all. It can be supervised or unsupervised. So we support a variety of unsupervised models built in. And all of these things like k-means, truncated SVD, or some aggregator stuff, isolation force anomaly. But maybe we're just doing supervised. And if you're doing supervised, you need to select your target. So we go down and select, well, we're trying to figure out for this credit card data set, whether or not the person is going to default on their payment next month from the given data of whether they've been paying, their age, and stuff like that. And this is the classic non-wizard view of driverless. It's a little bit dense, which is why we think the wizard is quite useful for anybody who wants to learn more about data science or wants an easier experience of setting up driverless. The wizard is very good. It's growing quite quickly and it does a lot of things, helps you. Let me turn off this sound. And it's better, and the wizard is also good in the sense that it avoids overwhelming you. But in this old classic view, you can see that you can choose a variety of things. And what should I do next? Well, that's what I want to think about. It looks like I can choose a time column, but I'm not going to choose time column from this data set. I can control the accuracy, which really just means choosing how confident you want to be in the accuracy. So it's a little bit confusing. That's why, again, the wizard is useful. You control how long you want to spend on this process. And you can, if you go to a different dialog, you can choose just how long in hours or minutes. And this interpretability dial will control how many features there are. So more interpretable will be fewer features, more likely to be a GLM, for example, to be more interpretable. And you can choose which metric you have. Here we have just AUC. And you can choose what kind of problem type you have. And over here, we'll provide you with a preview to tell you, well, given these accuracy and the data, we'll build a GLM, we'll do a light GBM, XGBoost, we'll do threefold cross-validation. We'll finally, in the final model, we'll blend them up. And we'll tell you a little about the features. We're going to build target encoding, clustering, frequency encoding, interactions between features, like plus and minus and divide. We'll do one-hot encoding and weight of evidence. And we'll treat the feature just as it was, a numeric feature. And so if we go with that, we launch. You could either launch it by selecting the experiment, or if I repeat it, so it can go, and I can actually launch a leaderboard. I won't do that at the moment, but I could have clicked this and it would launch 10 experiments at the same time, and you can study in a project how well they do. So let me go back to this one. So that's nice. So then let me finish real quick. So it's showing the accuracy again over here. It's showing you variable importance, what kind of features, like one-hot encoding. Maybe it did an aggregation transformation. So let's let that complete. It's relatively quick. I didn't try to get it to improve the accuracy, but that's basically what the tool is doing. It eventually is going to search for the accuracy like I showed in the other picture. And what I want to shift to is, now that you have a model and you've believed it's accurate, like I showed over here, you have something that's improved, it's the AutoML tool. Well, what do you do with it? And how can you go further? So if we let this finish up, one of the things you can do with driverless is not only look at data sets, visualizations, manage your experiments, including with the whole project view, share them with other people in the project, but you can also interpret the experiments, which I won't get into in this talk, but I will talk about this thing called recipes. So I'll just cancel this auto report since I'm not going to show that either. So we're done here. Now, what can I do? Well, I can continue tuning the experiment. That's one thing I can do. And what I'll focus on in this talk is what we call recipes in general. So what you can do with an experiment, you can actually create a recipe out of the experiment, upload it, we'll validate the recipe, and you can write your own recipes. This is arbitrary Python code. It's a little bit small font. I apologize for that. It's arbitrary Python code that for any experiment within driverless, time series, whatever, you have the full code for how to control the every detail. The model hyperparameters. So for example, let me show that. Yeah, down here. So the model type here is, if you can see this, is like GBM, the model parameters, and every single feature that we create down here is listed. We have columns that take in pay 0, education, and you, if you want, you can say, well, I don't want to use, for example, out of all these features, sex. I don't want to be biased against that. There's different perspectives. You could say you need to force that in to see how biased your model is, or you need to remove it so that your model isn't biased. But let's just say that you want to remove it. So I removed that feature, and then I can save that feature. And now I have a new recipe, which then if I do more actions and I use it in a new experiment, over here, you'll notice in the preview, it's talking about custom individuals. So this is a custom, what we call custom individual recipe. And and it lists the individuals here. It has a funny name because it was auto-generated. And if I launch this, then I'm guaranteed that it won't use that feature. And not only can you remove features or do little tweaks to the hyperparameters, you can add features. You can do pretty much anything you want. So this is what we call per feature control. This allows you to take any experiment and do it's just Python code. You can do loops. You can do anything you want in this Python code. So let's go back to that. This would be in the morning here, 8 a.m. This one. So you can do anything you want in this arbitrary Python code. It's just a class, and if you're good at Python, this gives you that access. So suppose that you want to do more, and you don't want to just control the experiment, you want to modify the type of model that you have because you have some domain expertise. You can do that. So for example, just to show you one recipe, this is I'm not sure if I can make this bigger. Let me go to the actual talk where I have this one zoomed in a little bit. Here. So this is again what we call a recipe, and you can edit arbitrary Python code and upload it to driverless. It will have, it could be in this case doing a custom model that even uses our own internal driverless stuff. You can reuse our own stuff, and we have about 200 or 250 recipes online that allow you to see examples of all this. This is a custom model, and it's basically just doing a custom objective. The objective happens to be some asymmetric objective. But you can see it's just kind of simple Python code. It's not that long, and you can do this too. You can write an arbitrary model yourself, and it may have domains, it may have specific features in there that are expected, and you can use those features. You can do a lot of powerful stuff with an arbitrary model in driverless. We call that model recipe. Another type of recipe is a transformer. I guess I'll show a slightly different one. Recipe log transformer. Yeah, so this is quite short, and it also builds the Mojo, the Java code. But I'll again show that in the other view so that you can actually see it a little bit better. Let's see, it's right here. So this shows you a very simple, it just takes the log of the input, and it's in data tables, so it's really fast. Data tables are our own, it's an open source product, but we built it with our team at H2O. But you can use pandas, it's fine. You can also import arbitrary packages in any of these kind of recipes, as if you were pip installing. You can also, for models and data recipes, I'll show data recipes in a moment, you can even have an arbitrary environment, which is totally different from driverless. So it gives you full capability. And there are examples on the website we have for that. So we have this website called H2O.ai Driverless AI recipes, which is open source. There's a huge number of types of recipes, like the individual recipes I showed. There are model recipes, like I showed, the transformer, like that log transformer, and there are data recipes. So a data recipe, one of the last things I'll show, is like this one. So let's do this. So in this case, what's interesting is I'm showing that you can even download data through some safe, secure URL. It could be internally within your company, and you can create data. And this can change the number of rows. It can do basically anything. And it's still just arbitrary Python code that it could have even its own environment. It's quite flexible. So the recipes are quite extensive, and this is another tool that Driverless gives you for basically making it possible to customize things for your domain specific needs. So let me wrap up. So in summary, AutoML helps by automatically, efficiently, reliably exploring all your options, basically. And you want to balance, I didn't go into the details of this, but you might want to focus on interpretability. And in that case, you might want to reduce the number of features. And we make that easy in Driverless AI by either the interpretability dial, and you can raise that up, and we'll automatically kind of do a good idea of what we should be doing, like focusing on a single model, GLM, a few features, simple features, or you can fully control it with that custom individual, or you can go to, I didn't show it, the expert panel, where you can basically control all of Driverless from the UI. You don't have to do Python code. And the wizard helps with that, like Arno showed before in one of the other talks as well. It needs to handle diverse situations and find the balance between all the kind of issues, and it should avoid making mistakes. So as I mentioned, Driverless AI is one of the best, especially compared to open source tools, one of the best tools out there. It helps you avoid that risk of the model ending up as one of the worst, and that's a good thing. And finally, it helps you explore all possible custom things. You can have custom models. I didn't go into custom metrics, but you can choose how to optimize your model arbitrarily. And this really helps you dig into your domain expertise problems with whatever specifics you have. Okay, that's it. Thank you, guys.